You've heard all the hype about quantum computers, right? How they're going to change everything. But they have this one massive Achilles heel. Well, today we're diving into a huge breakthrough from the University of Oxford. It's a totally new way to see the quantum world, and it might just be the key to solving quantum computing's single biggest problem.
So let's just get right to it. Why are these incredibly powerful machines so delicate? We hear all about their amazing potential, but what's really holding them back from being everywhere? Turns out it all boils down to one single persistent challenge.
And that challenge, that hurdle, has a name: quantum decoherence. For decades, this has been the roadblock, the thing limiting what quantum computers can do. And physicists have been on this relentless search for a way around it. So what is decoherence anyway? Well, in a nutshell, it's when a quantum bit, a qubit, gets knocked around by its environment. We're talking tiny vibrations, little changes in temperature, you name it. All that stuff messes with its special quantum state. The best analogy? Imagine trying to hear a tiny whisper during a full-blown rock concert. There's just no way, right? The noise of the concert, the environment, it just scrambles the information completely. That's decoherence. So to fight all that noise, scientists have been on this kind of quest, hunting for a holy grail material, a substance that can naturally protect that quantum whisper, something that could make it clear enough to hear above the roar of the concert. And that holy grail material has a name: a topological superconductor. Now, this is a really unique kind of quantum matter. The whole idea is that it hosts these exotic particles. And here's the kicker: these particles could store information in their actual shape. Think about that for a second. That would make the information inherently stable and way more resistant to all that outside noise. And this comparison just makes it so clear. A standard qubit is super fragile. Its information can be corrupted in an instant. But a topological qubit, it's robust. I love this analogy. It's like storing information as a knot in a rope. You can shake that rope, you can jiggle it around all you want, but the knot itself, the information, it stays stable. That is the absolute game-changing promise.
So this sounds amazing. Problem solved, right? Well, not so fast. There's been a massive catch. For decades, these incredible materials have been almost entirely theoretical. The problem wasn't the idea. The idea was great. The problem was we had no way to actually find one and prove, without a doubt, that it was the real deal.
Until now. And this is where our story takes a turn. A team at the University of Oxford has developed what is essentially a new quantum lens, a powerful new technique that can finally see what we've been searching for all this time.
And here it is. This isn't a computer graphic, that's the actual machine. It's called an Andreev scanning tunneling microscope, or STM. And what's so incredible is that these researchers invented a completely new way to operate it, giving them an unprecedented power to hunt for these elusive materials. So how does it work? It's actually so elegant. First, it uses this incredibly sharp probe to scan a material atom by atom. Second, and this is the secret sauce, the big invention, it's specifically tuned to detect something called the topological surface state. You can think of that as the unmistakable electronic fingerprint of one of these materials. It allows them to finally, definitively say, yep, this is one of them.
Okay, so with their powerful new lens ready to go, the team pointed it at a prime suspect, a material called uranium ditelluride. Since it was first found back in 2019, scientists had a really strong hunch that this stuff might just be one of these special intrinsic topological superconductors.
And the verdict came in. It worked. The technique did exactly what the theories predicted it would. They found that fingerprint, they detected that topological state, and they confirmed for the very first time that yes, UT2 is an intrinsic topological superconductor. I mean, this was a huge moment.
But this is science, right? It's rarely that simple. The discovery came with a really fascinating and important twist.
So it turns out that while this material does host the exotic particles needed for a topological qubit, they exist in pairs that, well, they can't be separated from each other. And if you can't isolate them, you can't use them to store and manipulate individual bits of information. So it's the right class of material, but it's not quite the perfect configuration you'd need to actually build a quantum computer. So close. And this is where the story gets really, really exciting. Because the real breakthrough here isn't just about this one material. It's about the tool. It's about the lens itself and the new path it's opened up for finding many more materials, which could be the key to mass production. I mean, just look at these two paths. Until now, the main way forward was the artificial method. Think of what Microsoft has been doing. You have to build these incredibly complex, mind-bogglingly expensive structures to try and create these properties. But this new technique enables the intrinsic method. We can now search for simple materials that do this stuff naturally. It's a potential shortcut to making these topological qubits economically and at scale.
You can just feel the excitement in the words from the study's lead author, Dr. Shukyu Wang. She said this is a truly exciting moment. And it's not just an observation, it's the validation of a completely new way of seeing the quantum world. It's a technique that's going to make so many more discoveries possible.
And Professor Seamus Davis, the person who invented this new technique, really drives home the impact. He says this can massively accelerate the search. We're not just fumbling around in the dark anymore. We now have a targeted tool, a searchlight, to find the right materials and finally maybe unleash that quantum revolution.
So what's the big takeaway here? A search that's been going on for decades has just been given a massive upgrade. The hunt for the unbreakable qubit is officially on, and for the very first time, it feels like we actually have a map. So, the only question left is, what are we going to find with it and how soon?